Hello ladies and gentlemen, welcome to my presentation on lithographic additive manufacturing of defined open-porous tricalcium phosphate scaffolds. My name is Martin Schwentenwein and I'm from the company Lithos, located in Vienna, Austria. And I would like to start my talk by giving a very quick introduction to our company, who we are, what we're doing. Then a brief intro to tissue engineering, the discipline or the field where this particular work that I'm presenting today is targeted. And then I will be showing you the way how we are doing the 3D printing of this tricalcium phosphate scaffolds, and then of course also show the results on the characterization of this 3D printed TCP components. So our company Lithos, we are located in Austria. As mentioned, we're a spin-off of the TU Vienna, founded 10 years ago, so we have our 10th anniversary this fall, and in the meantime we've grown to almost 100 employees at four different locations here in Austria, in the US, and also in China. We have an installed base of also roughly 100 machines around the globe. And what's also interesting to point out here is that we, as a company, have a business model of being a technology provider. So we are developing the machinery for the 3D printing as well as the corresponding materials. And the focus of what we're doing is ceramic materials. So having said that, I would already like to move forward with the bigger picture of why we did this work that I'm presenting today. And the aim here is this probably well-known field of tissue engineering, which is a very interdisciplinary area between biology, medicine, but also engineering technologies such as material science. And the focus of my talk today is using 3D printing for preparing such scaffolds that are playing a key role in this tissue engineering approach. So the aim of tissue engineering is to maintain, restore, or even improve different biological tissues. And by using ceramic as a scaffold material, we are obviously targeting here bone replacement materials. And there are certain ceramics, like the tricalcium phosphate ceramic, that is the material of choice here, that have a very similar chemistry to the inorganic content of bone. So if you use that as an implant material, the human body is capable of resorbing that material and remodeling it into native bone tissue again. So this is obviously a very interesting candidate for bone replacement material. And by combining these very interesting material properties of the TCP with the design freedom of additive manufacturing, you're obviously able to really play around a lot with the resulting properties. So you can get to a defined interconnective porosity, so you can play around with the permeability, which is a key factor for the way cells can migrate and can adhere then in the scaffold. Obviously, it also has a strong effect on the strengths and mechanical performance of the resulting scaffolds, and also the resorption rate. The higher the specific surface area and the thinner the individual struts, the faster the scaffold can be degraded under physiological conditions. And the focus of the talk today will be on the mechanical properties, also on the preciseness or precision of the parts, not so much on biological topics. For those of you interested in that, I'll be sharing a recent publication on that towards the end of my talk, where you can also find out more about the characterization in that particular area. So moving forward to the actual 3D printing technique that we employed here, it's called LCM, which is an abbreviation for lithography-based ceramic manufacturing. And the basic concept here is we are using light, we're using the concept of photopolymerization to cure a photosensitive ceramic suspension. So a liquid which contains a very high amount of ceramic particles, roughly around 50 volume percent. And by selective exposure to light, as you can see here schematically, this happens from below. So we have below this material reservoir a light engine where we can shine a certain contour onto the material, and only in the areas where the material is exposed to light, it solidifies. And by doing that in a sequential manner, it's possible to end up with a three-dimensional object that is then during the printing process pulled up upwards the z-axis. When this process is done, we are not yet completely finished. So we do have a so-called green part, a composite of the ceramic particles and the photopolymer binder matrix. And in order to get rid of this binder matrix, we put the part into a conventional furnace, and by heating up, it's possible to remove this binder matrix, and we really end up with the final ceramic piece. That is, of course, also accompanied by a certain degree of shrinkage. For tricalcium phosphate, we are in the range of 15 to 20% linear shrinkage, which actually can be well controlled. So you are simply printing the parts larger in the green state, so that after sintering you have the right dimensions that you want to have. You will see later on that it's actually not that difficult to get to a good geometrically fit. The nice thing about lithographic printing in general is that you can really target very precise and complex designs, as shown here on this image, or also on the short video on the right hand side. So it's really possible to create porosity struts in an order of magnitude of 50 to 100 microns, and also do that in a very homogeneous manner throughout the whole part. So as you can see here, there's no clogging in the inner sections of the component. It's really interconnective, and also homogeneous pore size distribution throughout the part. And that was basically the starting concept we also used for this particular work here. Here we looked into two different types of designs: a classical lattice grid, as seen in the upper line, and also a so-called kagome-like lattice. And we played around with the overall porosity by keeping the diameter of the pores constant and increasing the width or the thickness of the struts. These designs were 3D printed and then later on debinded and sintered to end up with the ceramic pieces, which then were first investigated using computer tomography in order to see if we were able to really replicate the targeted designs. We did some actual target comparisons. You can see here that there were some minor mismatches, which comes from a phenomenon called light scattering that happens when light interacts with particles, as it's obviously happening when you're printing ceramic suspension lithographically, but not in a very significant manner. So that are certainly things that could be compensated or can be compensated by software algorithms. So in this case, we used the parts as they were, because on the one hand they were a good fit, and on the other hand we could use the real density, because we had the results from this CT measurements. So this was no issue at all. We also checked the density of the material, so not the overall design, but really of the material. So the density in the strut, which was quite high, between 98 and 99% relative density. And then we used the different designs and moved forward with mechanical characterization. And for these highly porous structures, we were using compression tests and unsurprisingly, we found out that for the reference sample, which was just solid cuboid, we could get to the highest compression strengths, but also for, especially for the grid-like structures, we could get to quite nice strengths, so compression strength of roughly 45 megapascal for this grid-like design with 50 volume percent of porosity, which is actually quite good approximation to what you can also find in bone, as you will see later on. Here is just some data on the experiments. So you can see here also some images of the fractured parts. So for this Kagome type designs, you can see that the fracture was preferentially along the planes in the different in this tilting angle of the lattice, and for the grid-like structure it was more randomized, which might have played a role in this difference of mechanical properties. Yeah, sorry for this here. So this axis here obviously is the stress in megapascals, and here on the x-axis is the strain as indicated. And here is the mentioned comparison to the bone material, the native bone tissue, so the benchmark, the gold standard, obviously. And you can see that it's actually a quite nice approximation. We're not too far away. So here we do have the cancellous bone, so the spongy bone with a high porosity, and here the more rigid cortical bone. And depending on the way we design the scaffolds, it's possible to get to very reasonable approximations with a good fit in terms of density as well as compression properties. So to sum up things, it was possible to, on the one hand, use tricalcium phosphate, so a ceramic that is very similar to bone tissue, and used it for lithographic 3D printing. We could get to very high relative density inside the struts, and it was also possible to get to a very nice reproducibility. So the pore sizes and the porosity only showed very low deviations. Also the nominal target comparisons were quite nice, as I already mentioned earlier. Here for sure it's also possible by further improving that using software algorithms. The strength was in a range similar to what you find in native bone tissue, but on the lower end of it. So depending on the density between 6 and 45 megapascals. And as I said during the beginning, because of time constraints, I was focusing here on the mechanical performance and left out the biological data. So if you're interested in seeing and reading more about that, here I referred a paper from this collaboration where I also took the materials that I showed during this presentation. And of course there's also some further work planned, especially on long-term stability, also cyclic stress, so what an effect this will have on the performance and the properties of the 3D printed TCP scaffolds. And with this, I'm at the end of my presentation, and I would like to point out the collaborators here, which was Christina Schmid-Leitner, who did her diploma thesis on this topic, and Deepa Kalaskar from the University College London, And of course, thank you for your kind attention, and bye bye.